Hello. A very warm good evening to all amazing people who have joined us as companions on this wonderful journey to explore the world beyond our solar system. So, to share a token of commitment, we are back as promised last Friday with a very special speaker in the third lecture of this series on solar system. This lecture series is proudly hosted by Physical Sciences Consultorium. Physical Sciences Consultorium is a consortium of experienced professionals to offer our expertise to educational institutions, industrial organizations, and newcomers to encourage innovation, build collaboration, and mitigate confusion. Science for Everyone is the co-host of this initiative and a permanent partner of Physical Sciences Consultorium in science outreach activities. Science for Everyone is a dedicated science outreach platform. It aims to become a bridge between young students and experienced professionals. It works for popularization of science and aims to connect with people from diverse fields in a holistic approach. With this brief introduction of the initiative and hosting platform, I welcome you all this evening to be part of this exploration. Now, I take this opportunity to invite the chairperson of this lecture series, Professor B.M. Dixit, to chair the session. Professor Dixit is Professor of Physics and Director of Institute of Natural Sciences and Humanities at Sri Ramsarup Memorial University, Lucknow. Dear sir, I am humbled by your esteemed presence. I request you for welcome address to this gathering of inquisitive people ready to push boundaries to answer.
Okay.
Over to you, sir.
Okay. Thank you, Lalit. Am I audible first? Am I audible?
Yes, sir. Yes,
Okay.
sir. Yes, sir. You are audible.
Okay. So we are in this third lecture of the series of we call Know Our Solar System. Very aptly hosted and very effectively hosted by Physical Sciences Consultorium and Science for Everyone. My colleague, my very, what you can say, very personal friend, Lalit. He has brought this whole idea of bringing really experts from across the globe who are doing pioneer work, trying to see the unseen and letting us interact with those scientists who are really what you can say the future torch bearers of our great endurance, what you can say endurance, you can say journey of what we call science. We never know that whose contribution is going to contribute in what fashion in the future. As far as we individuals are concerned, we know few things here and there, but it is certainly not possible for any human to know almost everything that is around us. So, still to insatiate our learning trust, we can hold these type of meetings, we can hold these type of interaction, and that results into we without knowing so many things but listening from some expert, we will certainly get benefited by that. And I'm quite sure that the next hour or so would be a very interesting journey as Dr. Priyanka from very prestigious institution from Germany working in this area of exploration of space in a very general way. Specifically, we talk about then our planetary science, solar system analysis, solar system uh, understanding of solar system. Then still further, if you try to demarcate it, then probably it would be a little difficult for all of us, our commoners, to understand that what exactly area wherein some experts are working. Because science specialized after level 1 or 2, that it would be very difficult for an outsider to claim and start speaking about that area. So we have with us today Dr. Priyanka, and Dr. Priyanka will take us to a voyage, a journey beyond solar system. So if you relate the 3 earlier lectures, we are going away from sun to the outer space. I am really very fond of listening stories. So for me, whatever Dr. Priyanka is going to talk about science, I derive few ideas from that from a storytelling perspective. Though I also belong to a community which deals in all these interdisciplinary situations, when we deal in elementary particle physics, when we deal in what you can say nuclear physics, so there is an energy difference by which we demarcate these 2 branches of knowledge. But anyway, ultimately, if energy considerations have been removed, then probably one complements other, both are complementary to each other. So I'm very interested to see that in next 1 hour, how far we are going beyond our solar system. So I welcome Dr. Priyanka, and I am really very, very thankful to all who have joined us in this very specific prime time discussion at 8 p.m. on Friday, Indian Standard Time, when there are so many things happening around. But yes, it would be available at YouTube, so you can later on, one can visualize, one can visit it and see what we have discussed today. But I am quite sure that next 1 hour would be very, very interesting. So I am welcoming Lalit back to take this program further, and I am now a very keen listener. Thank you very much.
Thank you, sir, for this welcome address. Now, to proceed further, I take this opportunity to welcome our speaker. So it is very special for me to introduce our invited speaker for today's session. Dr. Priyanka Chaturvedi is with us from Thüringer State Observatory, Germany. Thank you, Dr. Priyanka, for being with us. It is my pleasure to introduce you on this platform. Dr. Priyanka Chaturvedi obtained her bachelor's degree of science in physics from iconic Ferguson College in Pune, now Ferguson University, and a master's degree in physics from Department of Physics, University of Pune, now known as Savitribai Phule, Pune University. For her doctoral thesis, she joined Astronomy and Astrophysics Research Group at the Physical Research Laboratory at Ahmedabad in India. She got a PhD for her work on radial velocity studies of eclipsing binary systems in the year 2016 and received K.D. Abhyankar Best Thesis Presentation Award at ASI 2017 meeting Jaipur. Before joining Thüringer State Observatory, Tautenburg, Germany, as postdoctoral fellow, he worked at prestigious Dhaka Institute of Fundamental Research in Mumbai for a year. She has published and presented her work at various national and international forums. Also, she is the principal investigator for low mass star and eclipsing binaries initiative with Spectrographs, a unique facility designed and developed in India, which was in news in June 2018 for India to join elite exoplanet hunt club. She is currently working with the CARMENES project funded by DFG grant at TLS. Apart from active engagement in research activities, Dr. Priyanka trains newcomers and encourages science outreach activities with active participation. She is a junior member of International Astronomical Union and member of Astronomical Society of India (ASI) and the United Science Forum, a wonderful initiative to promote science among masses. I have been lucky to know her as a multidimensional, compassionate senior who taught how to celebrate life without while exploring its challenges by living it. I offer my sincere gratitude to you for accepting this invitation and taking precious time from your busy schedule for being with us. I take this opportunity to invite you for presentation. Please take over.
Thank you, Lalit. Thank you, Lalit, for this nice introduction. Can I share my slides?
Yeah, this is the slide. Your screen is shared here. You please open your presentation and we'll be able to see it. Yeah, it is working fine.
Okay. So thank you, Lalit and Deekshit sir, for the nice welcome and introduction. And also thank you very much for organizing this nice lecture series. I have been following this lecture series for the past 3 weeks, and there have been amazing talks by Kuljit ma'am, Ritesh sir, Vagish, and Manish. So they have made my life a bit simpler. So in the previous talks, you all would have heard about our solar system and sun. And now I would want you to take you on a journey on beyond our solar system. So basically the lockdown has really locked us all and we can't travel, but I think I can take this opportunity to take you online on a journey. So what I'm going to talk about is what is an exoplanet? Why do we search for exoplanets? How do we detect it? And what have we achieved so far in this research area? So I think this is a very interesting topic for most of us, even for people who do not do research in this area, amateurs alike. They find this pretty interesting. What is actually an exoplanet? So technically speaking, all of the planets in our solar system, which are not orbiting sun, they are called as exoplanets. So we already know that there are 8 planets in our solar system. And all of these planets orbit the single star that we have in our solar system, which is the sun. But if there are planets which are orbiting other stars, then these are called exoplanets. I mean, it would be very common for you maybe to look above the skies in the night sky. You would have easily identified many stars in the sky, and you would have come across many constellations. And maybe you would have also seen this constellation, which is called as Orion. Orion, जिसे हिंदी में शिकारी कहते हैं या फिर इसे मृग नक्षत्र के साथ भी एसोसिएट किया जाता है. So as you see in this diagram, there are 2 very prominent stars. Maybe you would have seen them already. One of them is Betelgeuse. इसे संस्कृत नाम है इसका आर्द्रा. and the other one is Rigel. Iska Sanskrit naam hai Rajanya. So if you would have carefully noticed, these stars have a color associated with it. So normally stars are point source, yes, apart from sun, which is so close. That's why you can angularly resolve it. You can see it as a disk. Apart, all the stars appear like point source, but they are not really white in color. Not all are white in color. Some of them have some other colors associated with it. So like the Betelgeuse, this has a reddish tinge, a reddish hue associated. Whereas if you go to Rigel, the other star, Rigel has a bluish white color associated with it. So are we the first ones who are talking about colors in stars? No, not at all. And what do these colors talk about? Okay, so let me show you this HR diagram. So people who know a bit of astronomy would have already known about this. This is the Hertzsprung-Russell diagram. So there were two astronomers who were also curious, and they discussed about similar stuff that we are talking about. What do these stars have colors for? Are they really stars of different colors? So what they plotted on this map are various stars of different colors and luminosity. So on the y-axis, there is luminosity. So what is luminosity? Brightness. यानी एक star से कितनी light आ रही है, वो कितना चमकीला है. So if a star is very very bright, it would have a higher luminosity. तो यहाँ पे जो axis पे 1 है, that refers to the solar luminosity. And this is higher than solar luminosity, and this part of the axis are stars which are less luminous than sun. X-axis पर है temperature. Now what does a temperature in a star mean? We are talking about the surface temperature. The surface of the sun that we see, it has a temperature of around 5800 degree Kelvin. अगर आपको डिग्री केल्विन और डिग्री सेल्सियस के बीच का फर्क नहीं पता, तो मैं आपको बता देती हूँ कि नॉर्मली इंडिया में अभी आप अपने जो रूम्स में बैठे होंगे, आपका टेम्परेचर लगभग 25 से 27 डिग्री सेंटीग्रेड होगा. मतलब जर्मनी में थोड़ा ठंडा है, बट इंडिया में नॉर्मली 25 से 27 डिग्री सेंटीग्रेड. Yes, it is very hot. But if you think that sun is really very hot, then just look at this diagram. ये जो स्ट्रिप यहाँ पे दिख रही है, इसको हम लोग मेन सीक्वेंस स्ट्रिप कहते हैं. So what this main sequence strip is, these are stars which are burning hydrogen into helium. So these stars are of a particular age wherein it is possible for stars to fuse hydrogen and convert it into helium. We all know that stars emit light, and they produce this light inside their core. And this is the time when they are producing this light. Now, when stars are forming, it's not always true that stars have the same size. They could have different sizes. So stars which are very big in size, which are very luminous and have a very high temperature, they appear bluish white in color. They sit here in the diagram on the upper left corner. So these stars have a higher luminosity than sun, and they also have a temperature which is pretty high. Now, stars are classified based on the temperature, and they are classified and they are associated with spectral types. Now, these spectral types, so stars which are very hot on the main sequence part, they are known as O and B spectral type stars. Then as you come towards the sun, it lies almost in the middle of this main sequence strip. So sun is actually a medium-sized star, and it also has a medium kind of temperature. So it's not so hot and not so cold. Because as you see on the right part of the diagram, there are stars which also have a temperature which is less than sun, and they are also smaller in size. So smaller in size, that's why the luminosity is less. यानी वो कम bright है. And they have a lesser temperature, which is around 2500 degree Kelvin. Now, you would have also noticed that there are some stars which are present on the other part of the diagram, apart from the main sequence strip. So these are the giants, the supergiants, and the white dwarfs. Now, what are these stars? So these stars are basically stages of evolution of a star. So normally when a star is born, it takes a particular path, and it burns hydrogen, it converts it into helium, then it burns the heavier elements, and then it evolves, it grows into a giant, or if it is very massive, it would grow into a supergiant, and later on it would convert into a neutron star or a black hole based upon its mass. I'm not going to really discuss everything about stellar evolution, but it is very important for us to know that there are different kinds of stars present in our galaxy. Now, you would be wondering, how do astronomers know so much about it? कि एक star अभी पैदा हुआ, उसके बाद वो giant बना, super giant बना. I mean, this process takes millions of years. How is it possible to study this? I mean, just imagine, analogous example. If there is an alien who wants to know about the human race, what would he do? Do you think he would spend like 80 to 100 years on Earth knowing about humans? Probably not. He doesn't have to do this. The simple exercise which the alien has to do is he has to gather a larger sample of human beings. He wants to know how young the youngest human being can be, how old and oldest human being can be, what kinds of different heights the human beings can be. बहुत सारे human beings को एक साथ इकट्ठा करो, and then he can just look and see, okay, so okay, this is how a youngest baby is born, and then it grows and evolves into an adult, and then it gets aged. So if you have a bigger sample of human beings, you don't have to really spend 80 or 100 years to know how a human being evolves. This is what astronomers also do. We don't really wait for millions of years to study how a star evolves, but we try to take observations of many stars. And when we take observations of many stars, we come to know that there are various kinds of stars. Some of them are young, some of them are old, some are small, and some are large. So this gives us an idea about how they would be forming. So this is a very interesting concept in astronomy, when you make large sets of observations and try to draw a conclusion. So this is not just restricted to stars, but it also gets translated to planets. I mean, you have such an amazing plethora of stars which are present in the galaxy. Wouldn't you wonder, are there no planets? So this brings us to the second question. Why do we search for exoplanets? I mean, I think this is the first thing which would interest somebody. We are living on Earth, and of course, we are exhausting our resources and everything, and those are the other issues we don't want to talk about in this talk. But there is something which intrigues astronomers or people in general. Aren't there other planets which are present across different stars? How can we look for them? How can we search for them? And this was done for a very long time. Just to put things in context, I would like to say that astronomers believe that there are 200 billions of galaxies in the universe. Galaxy मतलब आकाश गंगा. जैसे हमारी एक मिल्की वे है, ऐसे 200 billion galaxies हैं. And each galaxy hosts around thousands of millions of stars. Now imagine, 1 million has 7 zeros. Can you imagine there are so many stars in the sky? And each of these stars could potentially hold a planet. This is amazing. I mean, if you come to know that this is the statistics that you're going to deal with, then you should be able to find planets. But then there are not so many planets that are detected because there are challenges in finding them. We would look up to what are the challenges in finding planets. So let's proceed. Now, the first discovered planet was in the year 1992 around a pulsar. So a pulsar is actually a magnetic neutron star. Neutron star is an evolutionary stage of a star. So it is like a dead star. It is at the later stage of evolution. And a neutron star basically emits pulsations, magnetic pulsations of electromagnetic radiations at fixed intervals of time. And there was a modulation, change of pattern in these pulses, which made astronomers Alexander Wolfskin and Fred in the year 1992 to find 2 planets across this dead star. So this was the first exoplanetary system detected. This was amazing, but what followed was more amazing. So what was next was the first one, which was discovered across a sun-like star. So there is this star 51 Pegasi b, which is also very much like Sun. It is a G-type spectral star. And the first exoplanet was discovered by Michel Mayor and Didier Queloz in the year 1995. For the same reason, they were awarded the Nobel Prize in Physics in the year 2019, which was announced in October last year. So what is special about this exoplanet system is that the mass of this planet, 51 Pegasi b, this is how you denote an exoplanet. So you call the star as by its name, and then you denote the first planet by adding an extra letter B to it. So if we have to talk about Earth, Earth is like the third planet from Sun. So it will be known as Sun D, small d. So 51 Pegasi b is the first planet found across the solar-like star 51 Pegasi. And the mass of this exoplanet is 0.46 times mass of Jupiter, roughly half the mass of Jupiter. But what was interesting was that the orbital period of this planet is 4.2 days. Now, at that time, when people were trying to search for exoplanets, this research was being done for like past 2 decades, and people were desperately trying to find exoplanets. But what knowledge we had previously, before we found another exoplanet, the only knowledge we had about a system was our own solar system. And in our own solar system, the closest planet that we have is Mercury, which is orbiting at a period of 88 days. And there are planets which go further beyond, like Earth has an orbital period of 365 days, and Neptune has like a few years. So there were planets which were orbiting at a further apart distance from the host star. But here they found a planet which was so close, so they would not believe the results. They were really intrigued. They did several tests, and finally they confirmed, no, this is not something spurious. This is not something wrong in our data, but what we found is actually a planet. And then these results were published. Followed by this interesting discovery, also other American astronomers, Geoff Massey and Paul Butler, also published their planets across 2 other stars, which were also orbiting in a small orbital period. So this confirmed that there are planets which orbit other stars in pretty shorter orbits. This was unseen before. This opened a new box of research. Like, we never thought there would be planets which would be orbiting so close to their host stars. And today, where are we? We have around more than 4,000 planets discovered. And most of them are very much different from our own solar system. So this is something very interesting, which happened 2.5 decades back. And we are still counting. Like, almost every day we have on the research archive, we keep on hearing about planets. And it's not just single planets. We also hear about multi-planet systems, like our solar system or close to a solar system, where you have more than one planet orbiting a single star. But what the aim is for astronomers is to find for planets in the habitable zone. Now, you would have heard about this word habitable zone or life on other planets. So let me tell you, for the moment, we have not detected life on any other planet. What we can find from here is biosignatures. I mean, we try to search for planets which would be in the habitable zone. Now, what is a habitable zone? I mean, there is an optimal distance from the parent star where a planet could exist and liquid water could be at the right state. I mean, if you happen to place a planet too close to a star, then it would be very hot. Like, Mercury doesn't lie in the habitable zone of Sun, because 88 days, and considering how much heat Sun emits, it is too hot for Mercury to be that close to the Sun. No life could ever exist on Mercury. So it does not lie in the habitable zone. If you talk about planets which are further out, they would be like ice. They would have ice on their surface. If there happens to be any water there, this would be in the frozen state. So you cannot expect any life at that planet as well. But if you talk about planets which happen to lie just at the right place, there is where we are talking about the habitable zone. And of course, Earth lies in the habitable zone, wherein we are at the right temperature, the right optimum temperature where life could exist. So it is very important. So that's what astronomers, people who search planets, they try to find out. Of course, in the course of finding such planets, you not only discover just habitable zone planets, but you find all kinds of planets, which are equally important, because before finding a planet so close to the sun, we had no idea that planets really exist that close. But having discovered such planets like the 151 Pegasi b, we came to know that there are also planets which exist so close to their parent stars. So now we talked about why it is important to search for exoplanets, but how do we detect these exoplanets? And that is where we researchers play or contribute our parts. Now, there are several ways to do that. One of them is the pulsar timing. The pulsar timing method was the way in which how the first planet was detected. So I already spoke about the planet, which was discovered in the year 1992 by Alexander Wolfskan. And this was how it was detected, because there was a difference in the pulses arriving and they could find that the planet existed. Then there are other common ways to search them. One is direct imaging, gravitational microlensing, transit method, and the Doppler method or the radial velocity method. I'm going to speak briefly about direct imaging and the transit method, and then I'm going to talk about the radial velocity method. So I basically work in this area. I try to search for planets by the radial velocity method. So I would also be talking about how do we do it. So let's begin with the first method, direct imaging method. Now, what do you mean by direct imaging? It's just like taking a photograph. So it sounds so simple, but it's actually very complicated. Why it is complicated? Because star has its own light and it's pretty bright, very bright. But if there is a planet, we all know that planets do not have any light of its own. Whatever light it has, it is reflected from its star, or it gets heated and it emits thermal radiation, but it doesn't have bright light. So it becomes very difficult if you want to image a planet in front of wherein there is a bright star which is just neighboring star across it. So this is very difficult to image a planet. Now, how do we do it? If you remember this in your geography lessons, you remember what happens during an eclipse. And during an eclipse, you have that when there is a solar eclipse, you simply have the moon which covers the sun. And when the sun's glare is covered, you are able to see this diffused emission surrounding the sun. And Vagish very nicely talked about this in his previous talk. So this is the corona of the sun. This is the outer atmosphere of the sun. This cannot be seen directly unless you are blocking this with the help of something. Here, naturally, moon comes and blocks the solar bright part, and we are able to see the corona. And similarly, if you happen to create an artificial disk or a star shade like a thing, and you cover your bright star, then you would be able to see something outside, which is the corona. Same technique is used to detect planets as well. So now it depends on which wavelength band you want to study. Now, light is an electromagnetic radiation, and on Earth, we get visible and infrared and radio as well. So if you want to look at a planet in the visible band, this would how it may look like. Even if there is a planet there, you wouldn't be able to see it clearly. But if you go to the infrared band, which is the redder part, then you can see that the planet is seen clearly. Why does this happen so? Because of the black body radiation. I mean, black body peaks at the wavelength based upon the temperature of the body. Since the planet has a lesser temperature, the black body peaks at infrared wavelength, which means the planet has a higher intensity in the infrared as compared to the visible. That's why it is easier to see the planet in the infrared wavelength band as compared to the visible wavelength band. So that's what astronomers do. They try to take the image of the planet in the infrared band, and they also use these star shades to do that. And we have amazing results. So this is a planet which was discovered by direct imaging method. This is Beta Pictoris b. So B again stands for the planet and Beta Pictoris stands for the star. So this is the name of the star. As you can see, there are several frames of the star planet system taken across time. So starting from the left top corner, the December 2014 image shows us the star, which is covered with the star shade. So the starlight is blocked. and you can see the planet seen here. And then over the time, the planet is moving in its orbit. So you see that the position of the planet keeps changing. Slowly, it is approaching the star. And when you see at September 2016 or October 2016, the planet is very close to the stellar disk. In November 2016, it's almost getting hidden by the disk. And for the 2 years, the planet was not seen. And suddenly in September 2018, it emerged back outside from this disk. So this was amazing. So the astronomers really followed this particular system for more than 4 years. So this is, I would say, a positive or a negative part of being an astronomer. You are dealing with events which occurs over few days and years, and you have to be really consistent and patient in making observations, and you have to repeat your work to be sure of what you're seeing is really a true signature of a planet or not, or something else. So this is the painstaking work which they did and confirmed that Beta Pictoris b is really a planet and it's moving in orbit across its star. So this was one of the directly imaged planet. Now let's go to the second method, which is the transit or the eclipse method. It's also called as the shadow method. Now, it's very easy to understand. So let me just show you. If you remember about this Venus transiting the sun, I mean, it's common that Venus or Mercury would transit the sun. Now, this is the disk of the sun. Since sun is very close to us, you can see this like a ball of gas. It's resolved in angular size. And then you see a planet, which is Venus, which is very small. It appears like a small black dot which crosses the sun. And this is the transit where Venus is transiting the sun. Similarly, other planets also transit other stars. And but the only difference is that we can see the sun we can resolve the sun. So you can see it like a ball, a real ball or a ball of gas. But other stars you just see as point sources. So you won't be able to see that something is black dot is crossing that star. That you won't be able to see because we cannot resolve other stars. But what you could do in principle is this, that suppose you have a graph wherein you plot your brightness or the luminosity versus time, how this changes over time. So if you have a planet which is present at this position, you would just get the total light coming from the star because nothing is blocked. As soon as the planet comes in front of the star, some portion of the light is getting blocked. And then you see that the total intensity starts getting dropped. It gets dropped till the planet is in the center, because now it's whatever the planet could cover, it has covered of the star. And then you see this portion wherein the minimum in the light curve is. And then again, when it leaves the stellar disk, you again see the increase in the brightness. So in order to easily explain, there is a movie I would like to show you. So this is when your star is orbiting the planet. On the left corner, just see how the graph is generated. This is because of the total intensity. And as soon as it passes the front of the solar disk, you see the dip in the curve. And when it goes back, you again see that the light goes back to its normal position. Now, this is just like when once this transit is happening. If you are able to record this again and again, you would be able to see that the transit happens at a fixed period, because the planet is orbiting the star at a fixed period. Let the period be 4.2 days, 11 days, or 12 days, whatever that number is. Every fixed amount of that period, the same phenomena will happen. The light curve will otherwise be straight, and at the same point, it will create a dip. So this is how astronomers look at planets and find out. Now, but what is something which is challenging is this, that a special geometry is needed for the transit. So if your planet is passing across the star in such a way, you can record the transit. But if your planet is face on, if it is passing in such a way that is just circling, but it's not happening to cross between you and the star, then there is no blockage of light, and then you cannot see the transit. So transit detection method only works in few parts. It doesn't work always, because then your planet, if it doesn't come between you and the star that you're observing, transit method would not work. So this particular method was used by two popular space missions, and some of you would have heard the names. The Kepler mission was a revolutionary mission. It was a NASA mission launched to detect exoplanet transits, and it did a marvelous job. It looked at thousands of stars and created many such light curves and found many planets, which were followed up by astronomers across the globe. It just concentrated on one part of the Milky Way, and there were many stars which were followed up by the same method. NASA mission Kepler was between 2009 and 2013, and then the mission got over. But then in 2018, there is another mission called the TESS mission. The TESS mission is also by NASA, and it is doing a similar job of finding planets across stars. The only difference is now that TESS looks for stars across the sky. It is not concentrated in just one region, but it looks across all parts of the sky. And it has an orbit of like 27 days. It looks at 27 days at one fixed portion of the sky, then it moves to another fixed portion. That's what it does. And another prominent difference between Kepler and TESS is that TESS is trying to look for brighter stars, but whereas Kepler was looking for fainter stars. Now, what makes it important? If you have brighter stars being monitored, then it will be easy to be followed by ground-based observatories. So the ultimate idea is to follow these stars from ground-based missions. If you want to look for fainter stars, it gets difficult because from ground, we are obstructed by the atmosphere and we cannot really go faint. And because atmosphere also scatters some light of the star. But so brighter stars are easy to be studied. Now, how do we study them in detail? So I told you that what we come to know from the transit of a star is that we are able to see how big the size of the planet is. So we are able to find the radius of the planet with this. But it is difficult to know the mass of the star from transits. So that this is where the Doppler or the radial velocity method comes into picture. And this is the method which I also use to search for exoplanets along with my team members. So what is the Doppler or the radial velocity method? So let us talk about first some basic concepts. So the first concept is here about the center of mass. So I am pretty sure most of you would have studied the center of mass in your school level physics. So center of mass is the place where you balance the particular object. So if you have two people sitting of 50 pounds separated by 10 feet distance, naturally the center of balance or center of mass is at the center of this position. But suppose if you change this picture and you have an adult and a child which are playing a seesaw or something, you would have easily noticed it gets difficult because the center of mass is now close to the adult. Because adult has a higher weight, 160 pounds or whatever, and the child has a lesser weight, the center of mass or center of balance is situated close to the adult. So this concept, when you extend it to the star-planet system, is also true. Colloquially, what we keep on speaking is that the planet goes around the sun or goes around the star. हम लोग ऐसे ही बोलते हैं ना, ग्रह घूमता है तारे के अराउंड, पृथ्वी घूमती है सूर्य के across. But the reality is that both planet and the star, they go around the common center of mass. And since the star is much heavier than the planet, the common center of mass is located very close to the parent star. And this is where the common center of mass is located for the star. So star also makes a small circle around the common center of mass, and planet makes a larger circle. But what we cannot see directly, the small circle, that's why we say that, okay, the planet is going around the star. But in reality, both the planet and star are going around the common center of mass. So the small circle which the star traces is known as a stellar wobble. And this stellar wobble is something that we astronomers want to detect in order to search for planets. Now, how do we observe this stellar wobble? So stellar wobble is it's very this Doppler effect or stellar wobble is similar like the Doppler effect in sound. So take an example of a car. let's say there are two observers. One is present here and one is present on the right side, one on the left and one on the right. And let's assume that the car is going in the right direction, towards the right side. So you would see, if the observer is present on the left, he would hear the fading away of the car sound when he's standing here. But if you are present on the right side, you would see that the sound which you're observing for the right side observer would have an increased volume or an increased frequency. So just speaking, the sound for the observer 1, it looks red because it's like faded away. And for the observer which is present on the right side, which is standing in the direction of the car, it looks blue, where the frequency is higher. Now, also you could have experienced the same thing when you are standing at the railway station, the train, when waiting for the train. When the train approaches and the driver blows the whistle of the train, you would see that when the train is approaching, the whistle gets louder or the frequency of the whistle increases. But when it goes away, it leaves the station, the frequency decreases. This is the Doppler effect in sound. Same Doppler effect also happens in light. And this is what happens in light when you have that your sun or your star is going around the common center of mass, and the planet is also going around the common center of mass. As the star is, as you see, is moving in the orbit, is coming towards you, the light that you see here is blue shifted. But when you see that the star is going away from you, the light that is coming from the star appears to be red shifted. So light, as you know, is white light, composes of several wavelengths. It's not just white light. We all know that one white light consists of many colors. And if the light is emitted by a source which is approaching you, this light appears to be bluish in color, and when it is going away from you, it appears to be reddish in color. And this concept is used to detect exoplanets. Now, how do we find exoplanets with this concept? So let's dig in a bit more deeper. We also, some of you would have studied in your school physics, in your 12th standard, about diffraction. The concept of diffraction is simple. If you have a prism and you have a white light, then based upon the refractive index and the wavelength disperses differently in different for different material, for different wavelength, the dispersion is different. That's why this light gets differentiated or split in this way, and you have a dispersion of the wavelength. So the white light, when passes through the prism, it is splitted into different colors or different wavelengths. Also, similar thing happens in a diffraction grating as well. So if you have a diffraction grating, maybe some of you would have done an experiment wherein you have a normal to the surface, and then you have a laser, you shine that laser and you see a first order diffraction, a second order diffraction, and in the center you see most of the light which is concentrated at the zeroth order or the central order. Now, diffraction concept is used in spectrographs to do the same. So you try to split your light, which is coming from the star, and you try to pass it through such diffraction gratings and prism and split it into such wavelengths. And how you do it? I mean, I would just put in few technicalities, not a lot. So don't get intimidated. Don't get afraid of these equations. I don't really want to derive or do anything, but just want to put couple of concepts straight. So this A is the angular dispersion, which is d beta by d lambda. Now your alpha is your incident angle at the diffraction grating, and beta is the diffraction angle. So how much you're able to diffract. So if I go previous slide, you see that the violet gets diffracted more than red. Right? So how much you're able to diffract depends upon the wavelength, of course. And if you want to be able to resolve two wavelengths nicely, if you want to really see how two wavelengths are separated in a nicer fashion, then you want this angular dispersion to be large. And for this angular dispersion to be large, your M also has to be large. And what is M? M is the order of diffraction. If you remember from your school or your college level experiments, your order of diffraction M actually most of the light gets concentrated at the 0th order. So if you do the diffraction experiment at the central order, you have the most light. And when you have the first order diffraction, the intensity of light decreases. At second order, it decreases further. So ideally, we want to do an experiment wherein we want a higher M, we want a very large angular separation, but we also do not want this intensity of light to go down. And there at this position, we use the Ishel gratings in litro configuration. So we try to change the angle of the diffraction grating in such a way that we make it similar to the angle of incidence, and this concept is called as litro configuration or blazing the Ishel grating. So these blazed Ishel gratings are used in all spectrographs which try to search for planets. And where are these spectrographs? So there are several spectrographs which are used across the world, and they try to search for planets. So like the 51 Pegasi B planet was found by Elodie. Then there are spectrographs like Sophie, Hertz, Espresso. But they are outside India. We also have spectrographs which are doing this kind of work in India, wherein I did my PhD from PRL. We have an amazing, nice telescope, 1 meter telescope in Mount Abu, Rajasthan. And there I worked with this nice instrument called Paras. This is a high resolution spectrograph. So high resolution means the resolving power is a very big number, which means you are able to separate two wavelengths at a very high angular separation. So you really can zoom into the wavelength. The wavelength coverage of the spectrograph is 3,800 to 9,000 angstrom, which means it is operated in the visible wavelength band. And this is the photo of how the spectrograph looks from inside. And these coverings that you see here are because this spectrograph is enclosed in a temperature and pressure stable environment. So to give you an idea, I mean, we were talking about searching for planets across these stars. We try to detect the small wobble, how small the wobble can be. So for the presence of a Jupiter around a sun, this wobble is like 12 meters per second. That is the kind of amplitude that you want to measure. That is still a big number. But if you want to detect an Earth across a sun, this number gets further small. It is just 9 centimeters per second. So if you have a smaller planet, then naturally the force that it is acting upon the parent star is small, and that's why the wobble is very small. So if you want to detect smaller planets, your instrument has to be very stable, and it's a engineering thing wherein we have to make it pressure and temperature stable. It is very, very important. So how does this spectra look like? This is how a raw spectra from an instrument looks like. So this is the data which is taken from the lamp. All the bright things that you see here are actually the wavelengths produced by the thorium spectral lamp. And what you see here, this is the spectra which is produced by the star, the continuous line that you see, and the neighboring light that you see is the spectra which is produced by the thorium. So this is how the raw data looks when you want to search for the planets with the radial velocity method. Then you finally do all the complex processes and you want to reduce this data. When you analyze and reduce this data, this is the final product. And this final product, on the y-axis, you have the flux, and on the x-axis, you have wavelength. And this is how the wavelength, the intensity versus wavelength diagram looks. So all these tiny wiggles that you see here, this is not noise, but these are elements which are present in the atmosphere of the star. So there are various elements, like you would have calcium, you would have hydrogen, there would be iron, nitrogen, all these elements would be present here. And these elements create these absorption signatures present. So if there were no elements, the spectra would be a straight line, a continuous line. But because there are elements present, you see these dips present in the light. And this is what we try to, since we now know that this is the wavelength at which the lines should be present, if they happen to shift their original positions, we try to search that, okay, because of the shift, there should be a presence of another planet. And then this is how a typical radial velocity curve looks like. And you try to plot and find out the mass of these objects. So This is the kind of research that goes into it. But what have we achieved so far in this research area? So we spoke about how it is done, but what are the achievements? What have we done so far? People across the globe are searching for exoplanets for such a long time. And in this diagram, I've plotted the mass of the planets which have been discovered till date, and this is the distance at which it is present. So the red planets are detected by the radial velocity method, the green ones are detected by transit, and the blue ones are detected by imaging. So you see the planets which are detected by imaging, they are present at a wider orbital separation, because if the planet and star are very close to each other, it becomes very difficult to find such planets. Whereas you see that some part of this diagram is still not complete, which means we do not have an idea of planets which have a lesser mass. So we are able to easily detect Jupiter mass planets, but detecting Earth-like planets is still a challenge. And the challenge is because there are several reasons for this challenge, because the Earth produces a very small signature on the star, and detecting the small signature is very difficult with the current instrumentation techniques. Then it's also possible that the stars would have its own intrinsic variation. So there are several things where one has to take care before finding such small Earth-like planets. But nevertheless, we have discovered many interesting cases. One of them is discovering the Earth-sized planet, which is present closest to a nearest star. So Proxima Centauri is just 4 light years away from Sun, and this happens to host a planet in the habitable zone. And the planet mass is 1.3 Earth mass, and it is orbiting at a distance of 11 days. And recently in January 2020, another team found out that there is another planet in this system, which is like 1900 days apart. So there is one planet which is 11 days far from Proxima Centauri, and there is another one which is like 1900 days apart. So there could be planets in such interesting systems which we have no idea. But what is more interesting is that the primary star, which is Proxima Centauri, is a M dwarf. So if you remember the HR diagram which I showed you initially, I talked about the less massive and the cooler stars. This is one of its kind. So Proxima Centauri is such a star. Then there was another batch, a largest batch of Earth-sized planets, which was found across Trappist1 system. So this was also around 2 years back, and the Trappist1 system is around 40 light years away. And the interesting thing is that 5 out of 7 planets, they are very similar to that of Earth, and they 3 orbit around the habitable zone. So to remind you, habitable zone is that optimum place from far from its host star, which could host liquid water in its liquid state, water in its liquid state, that optimum temperature. It doesn't mean that we have found life. It just means that the planet could exist in that particular state. Now, also there is an interesting aspect that there are most of the stars in the galaxies are M dwarfs. Around 75% of the stars are M dwarfs, the less cool ones, but they are not studied so well because they are small and they are faint. And if you try to look for how many planets have been discovered around these low mass stars, so there are less planets. So most of the planets have been discovered around solar mass stars. So if this is the planet mass plotted across the stellar mass, so this is one solar mass. Most of the planets have been discovered around solar type stars, because the surveys that are trying to look for planets, they are most sensitive to search for planets around solar-like stars. But still, there is a scarcity of planets around low-mass stars. And this scarcity is what we astronomers are now trying to fill in. So I currently work for this nice consortium called as Carmenes. It's a consortium between 2 countries, Germany and Spain. And we have like 11 partner institutes. And we are trying to find planets across such M dwarfs. And what have we found? We have 2 interesting discoveries. We have most Earth-like planets, which are 2 Earth-like planets. One is at a 5-day orbital period and 11.4 day orbital period around one of this star. and this is also very cool. Like Trappist1 System I talked about was a very cool type star. This is also a very cool type star, and it also lies in the habitable zone. So it is very interesting discovery. And we also found some other stars which challenge the planet formation models. And this was a giant planet found across a M dwarf, which is also very rare. And this was also a very interesting result. And what astronomers also try to now look for is, I mean, you are able to find out different planets around stars, but what is the next step? We are able to also search for exoplanets, atmospheres, and everything. But what next are we trying to look? So now astronomers try to find out signatures for life or biosignatures by studying the exoplanet atmosphere. And there are a variety of species that astronomers are targeting to look at. They're trying to find ozone, oxygen, water, methane, carbon dioxide, and such interesting things. And this is like the next step. And Hubble Space Telescope, Spitzer Telescope are contributing to these efforts, and the arrival of James Webb Space Telescope in 2021 hopefully would really change the scenario. We would be able to really understand more about the exoplanet atmosphere. So this is like the next steps which we are going to take in this field. So with this, I think I would like to stop. And this is the photograph of the telescope where I work in the observatory. So this is located in the central part of Germany. It's a very small place and with fewer people working, but it's a very, very beautiful place with a very nice telescope. It's a 2-meter telescope. And we also we take data with this telescope and also with the telescopes in Spain, which is in collaboration. And it has been a really exciting journey for me to work in this field, and I'm very, very happy to be able to share this work with you. So I think I would open the forum for questions and discussions. So over to you, Lalit and Dikshit sir.
Thank you so much. It was such a nice presentation. Now we are moving for question answer session. And we have requested from participants to put their questions on comment section so that we can take relevant questions in our available time for discussion. So there are a few questions we have on in the comment section. So I'm taking one of the questions. Yeah, this is a question by Abhay Pandey. He's asking, he wants to know about what we can say about temperature of the stars from which coming light suffers to Doppler effect. So probably he needs to know if light from stars, light coming from a star suffers from Doppler effect. Does it change when we look for temperature of the star? How does it affect it? It will be. I will be happy if you take this question and answer this.
Okay, so Abhay, thank you for the question. So if you are trying to look for the starlight, so the first thing when I showed you this constellation Orion and I spoke about Betelgeuse and Rigel, I talked that there are different colors associated to it. So one method to find the temperature of the star is to simply do photometry. Photometry means you just collect all the light which is coming from the star in different filters and you are able to find the temperature of the star. But when you do spectroscopy, which I do when we have to do the radial velocity method, it is splitting your light into different colors, like passing it through a prism or a diffraction grating. Now, there are several elements which are present in the star, and the presence of elements is like a signature for the temperature or the spectral type of the star. So if you suppose have a star which is very, very hot, then it would only have lines of hydrogen and helium present in it, which is also in the ionized state. But if you talk about stars which are cooler, like solar type stars, you would have other elements present in it, like iron or calcium or such elements. And if you talk about stars which are very, very cool, like the M dwarfs, this would have molecules which are present in it. So the spectra tells us a lot about different temperatures of the star. And when you have to search for exoplanets, currently the radial velocity method is more sensitive in temperatures between 4,000 to 7,000 degree Kelvin. And the reason is because these the stars which lie in this temperature range, they have more absorption features present. So it is easier to detect by the Doppler method because there are more absorption lines. So you are able to see how the lines shift. If you do not have lines to measure, then this method will not work. So radial velocity method will not work on hot stars. That's how temperature plays an important role here.
Okay, thank you so much. I think he got the answer for the question. And in continuation, I would like to add one question that when we are observing these stars, so we have different kind of observatories. We have some ground-based observatories, and sometimes we send some instruments on satellite to do this kind of observations. So why do we do it? Can you tell a little bit about that? It is a very popular kind of thing, and I think a lot of people will get an idea why we do these two kind of things.
Thank you, Lalit, for this question. It's a very nice question. Ground-based telescopes are in principle easier to build. I mean, you have all the facilities on the ground, you can transport everything, and even if something breaks, kuch galat ho jata hai, you can easily go and repair it. But if you have to send something in space, you have to be 100% sure that that thing is perfect. It works at those temperatures, and it works irrespective if there is sun in the sky and there is radiation and there are other hazards which are happening in the space. It should be taken care. So doing space instrumentation is a really challenging topic. This is a difficult part, but what's the benefit of being in space is that you avoid the atmosphere of Earth. If you are looking at any light which is passing from the atmosphere of Earth, then you have this effect of extinction, which means that the light gets redder. And also there is a lot of if you have looked at any star from Earth, you would see that the stars twinkle. Why do they twinkle? Because there is atmosphere. If you happen to be in space, there is no twinkle, twinkle, little star, because there is no twinkling. The twinkling happens because of the atmosphere. But this twinkle is nice in the poem. The problem when we astronomers want to focus the light on the fiber or anything or in any instrument, this becomes a challenge. If there is a lot of variation and there is a lot of atmospheric variations, then the result is not good. Beyond, even if you increase the size of the telescope, you're not going to get any better in collecting light. And at that point of time, you have to avoid the atmosphere. And in such a scenario, space-based telescopes play a good and important role. That's why Kepler and TESS satellites have been really amazing. And the other problem at being at ground is that you would have the day and night. So you cannot observe one star for a long time. But when you're in the space, if you're not facing the sun, you can look at the angle, like you can look at the position of the sky continuously for 24 hours without bothering about day and night. But we at Earth have to bother about day and night. So this is another good part of being in space. Yeah.
Okay. Thank you so much for answering it in such a nice way. And we have some few more questions from our audience. So let us see. This is one question from Shishir. He's asking, do most stars found in pair triplet in the Milky Way? And if so, how much do they affect, interfere the process of impact?
This is also a very nice question. Thank you for asking it. Yes, almost half the stars or more than half of the stars are speculated. They are thought to be that they would appear in pairs. Now, there are several discoveries where you have found an exoplanet which is actually orbiting two stars. So instead, like the Kepler-16 system, where you do not have a single star like Earth and a sun system, but it has two suns. So a single Earth and two suns system. This also exists. And detecting such systems becomes complex. Like if you want to search even for multi-planet systems, one challenge is that the radial velocity signal or any signal, it gets contaminated by the other planet or by the other star. So you have to really model that star or planet signal out if you want to find your other signal. So this modulation has to be considered, and therefore you need more data. So you need additional data, or you need data for a longer timeline in order to resolve such systems which have more than one star or which have more than one planets to model the orbit completely. Yeah.
Okay, thank you so much. And we can take one more question. It is from Prasad. He's asking, how would we confirm the life is there on or not on another planet?
I couldn't hear you. Could you please repeat the question?
Yeah, the question says, how would we confirm the life is there or not on another planet from the Earth?
Okay, so I mean, confirming life sitting at Earth is a very challenging thing. At the moment, you cannot be sure if life is present somewhere out. But what you could do is looking at biosignatures. Biosignatures means looking at elements which are present in the atmosphere of Earth, and you try to find similar elements in other exoplanet atmospheres. So first of all, searching for exoplanet atmospheres is difficult because these planets are really small, and the amount of light which is coming from the planet, even if you block the star or when you're looking at the spectra, this is very difficult. The number of photons are not enough. You have very little light which is coming. So this is a challenging thing. But if you happen to take such spectra, which is done now, then you can look for some elements which signify life. So suppose if you just find some oxygen in the atmosphere, you simply cannot say that you have found life, because there are several ways how oxygen would be formed. So if you have read the recent news that there was detection of phosphine in one of the atmospheres of the planet, and they say that this could be a possible signature of life. Why do they say so? Because the quantity in which they detect phosphine is about, like, at the right amount, which could only be produced by some activity like microorganisms which they produce on Earth. And that's how they get this idea that this could be possible, that there are some microorganisms. But we have no evidence of intelligent life yet on Earth. And the other challenge is, even if we find it, it's very difficult to travel that far, because these different planetary systems are really far away. But it's still interesting to know about and search for such signatures.
Okay, thank you so much. And there is a question relevant since we talked about these systems are too far, and there is a question from Prachi. She's asking which is the farthest exoplanet we have been able to detect in it. So maybe if you give some number, then get an idea.
I wouldn't remember any number. I don't know.
Yeah.
I mean, maybe I have to really look it up. The farthest we have gone like 150 light years away, and so, like, it's really far. But I don't know which is the furthest exoplanet that we have found. I know about the closest one, but the furthest one, it would be really faint. So you need very powerful telescopes and big instruments to detect that. But every day we are going far away, because we are improving the instrumentation. We have larger telescopes. So definitely it is going to be further away every day, I would say. Yeah.
Actually, we are having a lot of questions, and there is a limitation we have. We can't take too much question as of now. So we will look at this stream, and we'll get back to the people who are asking the questions, and we'll try to answer it in a way in comment section. Speaker, and other way we can share information to contact speaker for the particular question. If you have something interested, you can always write to us. We are sharing our contact details, so you can always write to us, and we will get back to you with answers from speaker. And so since we have a limitation of time, it was already 1 hour and 15 minutes. And so what I can do is now I invite our chairman, Professor B.M. Dixit, for his remark and comment on this session.
Okay. You see, I am still, you can say, thinking about something which is unthinkable. And Priyanka has taken us to some places which was always a sort of thing for human race since ages. I am telling. Why I am telling since ages? Because since long we are talking about that. Is there any system? Is there any intelligence system which is watching us, or we are the first to watch them? So this quest of mankind for looking for extraterrestrial life form, and this idea of searching life form in any planetary system is only possible because we all know that some stars are absolutely uninhabitable. So this search, this idea of defining exoplanet is a planetary system which is not going around sun is very what you can say very elementary definition. Why I am saying this is a very elementary definition? क्योंकि मुझे ये लगता है कि हम लोग बहुत सारी परिभाषाएं इसलिए बनाते हैं कि इसके सहारे हम दूसरों से बात करते समय चीजों को आसानी से रख पाएं। और एक्सोप्लैनेट कहना कि जो प्लैनेट्स नहीं है वो एक्सोप्लैनेट्स हैं, क्योंकि जो सन के चारों तरफ है उन्हें हमने प्लैनेट्स बोल रखा है और अपने सोलर सिस्टम के 8 मेंबर्स को हम लोग प्लैनेट्स के नाम से जानते हैं। दिस इज अ वेरी इंटरेस्टिंग नॉमेनक्लेचर, but beyond this nomenclature structure and the naming of the whole is what we call a subjective reality kind of a thing. There is a much beyond this, there is an objective reality. What we call objective reality is which is out of this human interventions. So there was a very big question that Einstein has asked against these quantum mechanics people, quantum theory people, that if the way you are suggesting the reality is, that means that whether moon exists is only because human exist in the earth. Because when we see, then only moon exists. This is how quantum mechanics brings the idea of quantum entanglement and so on and so forth. But what Priyanka has told us is that how science has started progressing with a very strong foundation of science, making smaller bits joining together, developing ideas which are very elementary, using Doppler effect, using this intensity variation through that sun transit method. These are all, if you look into the idea-wise, it is a very elementary idea. But those elementary ideas are leading us to a bigger quest of knowledge. Bigger mysteries are solved by these simpler things. That simply means that to do big things, you don't require a very complex understanding of the things. Things are rather simpler, and as Priyanka has already told us, that HR diagram, is very easy to think that yes, this is the main sequence, this is the white dwarf region, this is the supergiant giant star system, and then pointing out that there is a star, our star, in the main sequence region. But those two gentlemen have done extraordinary work to just draw that curve from by which we draw so many conclusions these days. So what they have utilized is a very simple idea. They have not done any complex things. They have done, Priyanka ma'am is the better person to explain us, that they have done only spectroscopic analysis, and they have started classifying stars in a particular positions, and then after some time they will start looking at that a diagram is appearing, and it was beautiful. Whosoever is doing a very elementary course of space science, star analysis, star evolution of a star course kind of a thing, then they will find that these are the starting, and this is probably the bread and butter of starting point of your astronomy course, the first basic course. तो ये यहाँ पर जो भी चीजें बताई जा रही हैं, जो भी चीजें कही जा रही हैं, अगर हम लोग ध्यान से देखेंगे, ये निसंदेह अद्भुत है। अद्भुत इसलिए है क्योंकि ये बहुत सिंपल है। अभी कुछ दिन पहले मैं थोड़ा एक सीरीज देख रहा था, that series was that series they are talking about this quantum secrets of life, and there they were trying to see that how quantum mechanics is completely manifest itself in all biological processes. So what I may seems to be a little digressed by bringing life form and quantum mechanics when we are dealing with astronomy and astrophysics and cosmology, but actually there are few fundamentals. If you have that understanding of those few fundamentals, they will be applicable almost everywhere in entire domain of science, and specifically in physical sciences specifically. So these ideas have been put forwarded by our speakers in such a fashion, and I'm very amused to see that few questions have come up which reflects that yes, it is people have taken interest into what Priyanka ma'am was suggesting to us, and if that is happening, that means the purpose of this type of meeting has been achieved. So I am really thankful, Dr. Priyanka, for such a wonderful presentation. You have shown us some really great, what you can say, I can say animation or video. I cannot demarcate between the two, but those things are that makes things a little bit easier to understand. Pedagogically, it makes the learning a little simpler. But to all my students who have listened, to all my friends who have listened to what Dr. Priyanka has said, is that humans have reached to some point, at least. They should feel good about it, that they are trying to resolve some issues which probably not created by their own mind. It is real problems. In psychology, in sociology, we try to figure out that what human has created, and human is facing the problems. But the way Priyanka has told us, we are doing something to unravel the mystery of the world, and the exoplanets is again a very interesting term. Lalit has already undergone that. Few of our students have gone on one of the projects in this exoplanet in our last undergraduate course. So exoplanet is taking up. Priyanka ma'am, you should feel very privileged that you are working on in an area which new students are taking up. That means it is going to take up in a nice way with the coming generation of people. Thank you, Lalit, and thank you, Priyanka ma'am, for such a wonderful illustration of the whole idea. Thank you very much.
Thank you, sir. It is a very good way we conducted the session, and the concluding remark is summarize things, how what we are doing, and with that, I would now, when we are moving towards in-depth session, I would love to express my sincere gratitude to Professor D.M. Dixit, sir, for chairing this session. Dear sir, your continuous support and mentorship is driving force for this ambitious journey of exploration. Thank you, sir, for being here and inspiring young people to do for a better world. With that, what we have for next week, I will be sharing some information about what we have to offer next week, and then we will close the session for today. And so, before I close this session for today, I would love to invite all of you who have joined us now, are those who will the next session of this series next week, on the next day, on the same day, at the same time, and at the same platform. So we have invited a very special speaker for next session to talk about Earth's sister planet Mars, exploring the question of habitability and its atmosphere. Today we have talked a little bit about the habitable zone, and there was some question. I hope those people will join us in next session, and they will get more information about what will be the habitability and the kind of life we are talking about. So we will be hosting Dr. Ashimananda Modak next week to add a milestone in this journey of exploration. It is going to be one of the best sessions of the series, so don't miss it. Signing off for today. Thank you all for joining us. See you next Friday. Thank you. Thank you very much.